Welcome to our next installment of Dive in 5 for grade 5. Today we'll be focusing on multiplication and division algorithms. My name is Barbara Knox.
And I'm Daryl Frost. Welcome.
Before we begin today, we would like you to pause the video and complete these two expressions on your own. Try to use 2 or 3 different strategies to solve each one of them. And think about the strategies that your students might use or strategies that you might be teaching them in the classroom and try to model some of those strategies. We'll see you back in a few minutes. As we look at the progression of the best standards, looking at 4th grade first in the blueprint, students worked with factors up to 12 with their basic multiplication and division facts. They multiplied whole numbers together, but they only worked with 3 digits up to 2 digits. In 5th grade, there is no limit on the number of digits in a multiplication problem. They also divided a whole number up to 4 digits by 1 digit, and in 5th grade, they will be dividing up to 5 digits by up to 2 digits with a remainder as a fractional part, just like it was in 4th grade.
So Barbara, I noticed something here and what you highlighted in green that we're focusing on here. I see the words a standard algorithm and both benchmarks and
Correct.
procedural fluency.
Yes.
So we're at that stage where they need to have, beyond just having a reliable strategy rooted in deep conceptual understanding, they need to now be very fluent.
Correct.
And flexible and be able to use any strategy given a context.
And that A standard algorithm doesn't mean that they need to use the traditional algorithm. They can choose an algorithm of their choice to build that procedural fluency.
Right.
Earlier this year, they did multiply and divide decimal numbers, and that kind of ties into what we're doing here with whole numbers in this unit. We are going to take a look at several different multiplication strategies and algorithms that they may be using in your 5th grade classroom. We'll tie everything back to those first 2 problems that you solved at the beginning of today's presentation. Here you see a base 10 model, a grouping model, where we have taken 16 groups and put 236 into each group. Daryl, where would this kind of learning have taken place?
Well, if I think back to maths, 4th graders would have done this. They would have created, worked with multiplication with multi-digit factors and created base 10 block models. Yes.
Correct. We're going to take a look at another base 10 model on the next slide. With this base 10 model, we have the 2 factors on the outside of the box. So I can see my factor of 16 on the left and my factor of 236 across the top.
Yes.
My students need to be thinking about, well, what are tens times hundreds? Thinking back to those patterns of multiplication. If I multiply a 10 times 100, I'm going to get what, Daryl?
I'm thinking 10 groups of 100, so it's going to be in the thousands.
Correct. So I've got 10 groups of 200, so I'm going to have 2,000.
2,000, yes.
And then I'm going to multiply my 10 groups of 300s, and I should get
10 groups of
10 groups of 3 tens.
10 groups of 3 tens would be 300.
300s. And finally, I'm going to multiply my 10 groups of 6 ones, which is going to give me
60 or 6 tens.
Correct. Then if I look at my next row, I have one group of everything. So one group of 200 is going to be
200.
And one group of 30 is going to be
30.
And one group of 6 is going to be
6.
And I'm going to repeat that 5 more times, right?
Yep. It's like repeated addition there.
This base 10 model will help students see the connection to the open area model. If I draw a box around my thousands, I have one section of my open area model, then my hundreds and my tens in that first, with the first factor partial product of 10.
Yes.
Right? And then I'm going to do the bottom section where I'm multiplying my ones, and again I have the hundreds, I have the tens, and I have the ones.
Right.
If I look at an open area model, you can see those factor or those partial products in the sections of the open area model.
Yeah.
I can see the 2000, I can see the 300 when I multiplied 10 groups of 30.
Mm-hmm.
I can see the 610s when I multiplied 10
60.
groups
Yeah.
of 6.
Mm-hmm.
Here I have my 1200,
yeah.
1800, and my 36.
Right. Yeah, that's a nice connection to see from that. You starting with the base 10 block, then you went to an open area model by making those rectangular, shape, you know what I'm trying to say.
Yes.
And then taking that to something more abstract with the partial products.
Right, and we're going to look at the connection between the open area model and the we're just seeing that when we use an open area model, we have to take all of those partial products and we have to add them back together to get our entire product. So moving on, we might do a partial products model where we're not using that open area model.
Let's see what
but
that
we
looks
want to
like.
make connections back to the open area model, right?
Okay.
So I know I've got 6 ones, and I'm multiplying those 6 ones times my 6 ones, which is going to give me what, Daryl?
36 ones, which
36
I see
ones.
that connection right there.
Yep.
Yeah.
And I'm visualizing back to that open area model of where that 6
I can see it in my head.
was.
I don't even have to have that there. I could see it because I've experienced it.
Then what am I going to multiply next?
Then I would consider, since that's 6 ones, 6 groups of 3 10s or 30, that's 180.
Okay. And from there, I would go to my 6 groups of 200.
Right, and I see it there.
And that is going to give me 1,200. So there are all of my partial products using 6 as one of my factors.
Then I'm going to move to 236 times 10. So I automatically think, well, I know multiplying by 10, that's going to be 2,360, but I see it decomposed over there. You're going to have 6 times 10, which is 60, 30 times 10, which is 300, and I see the 200 times 10, which is 2,000. I can see that in my head.
Correct, and we can make those connections back to that open area model.
Yeah.
So that they can see where all of those pieces were on the strategy that they've used in the past.
And once students understand that open area model, this will make so much more sense to them because they can see it. And then they will see the value in this.
Moving on to the more traditional algorithm, it becomes a little bit more abstract for students. They're learning procedures that are going to get them to a correct solution, but we want to make the connections back to that open area model and back to the partial products model so that they can see where the numbers are coming from as they're recording them in their traditional algorithm.
Yes.
I'm again going to start with 6 times 6. I get a product of 36, but I'm not going to record the whole 36 below the equal sign.
I need to regroup because I have to think about, okay, 36 is the product, but I have to regroup and get regroup 31s into 3 10s. So I have 6 ones left. Just there it is.
So there's my 36. I have my 3 10s above the 10s column and my 6 ones in the ones place. In the area model, I see that 36, the 3 10s and the 6 ones in that box represented by multiplying 6 times 6.
And then I see 6 groups of 30. That's 180. And that's not 3, that's 3 10s. That's a value of 30.
Correct.
So 180 plus 30 is 210.
And students might not see that right away. They'll get they multiply 6 times 3 and get 18 and add the 3 and get 21. They have to understand that that 21 represents 21 tens, and they might not understand where the 21 tens are in that open area model. But here I have my 18 tens and my 3 tens, and when I put them together, I get that 210.
Yes. My
last step with multiplying 6 is going to be to multiply 6 times the 2 in the hundreds place. So I'm going to get 12 hundreds, but I have 2 hundreds that were left over from the 21 tens, and I have to add that to the 1200s, which is going to give me 1400s.
Yep.
In my model, I should see the 1200s and the 200s that have been put together to make the 1400s.
Yeah, 1200 plus
200
plus 200
is giving me the 1400.
Yep.
When I move to multiplying times the 110, because I'm multiplying by tens, I'm not going to have any ones, because when we multiply by tens, we never have ones in our product.
Oh, that's so 6 times 10 is 60, yes?
Correct.
Well, I'm not adding a 0. I have 6 tens.
Correct.
So I need that's actually a place value position.
Exactly.
It's 0, 1, 6 tens.
Yes. And then I'm going to multiply my tens and my hundreds, and there is no regrouping in when I'm multiplying by 10, because none of them carry over into the next place value.
Yes.
When I'm finished, I have to add those parts together to get my final product, which is still going to be 3,776.
And we just have to make sure we ask connecting questions to
Yes.
these strategies.
Now we're going to take a look at the division algorithms and strategies. We're going to look first at using base 10 blocks to divide. So I'm going to start with my 7,000s, my 100, and my 11. I'm going to put them into how many groups, Daryl?
27 groups. That's
20.
My divisor.
Yes, so I have to make 27 groups out of these blocks. Right now, I don't have 27 thousands, so I'm going to have to regroup those thousands into hundreds.
Right.
So I'm going to go ahead and get out my 70 hundreds, which has the same value as the 7,000s.
Yes.
And now I can separate some of those into groups. I'm going to put 2 in each group, and I have some left over. I have 16 left over plus the 100 that I started with.
The 101, is it 101?
Yes.
Yes.
But I'm going to take all of the hundreds because I don't have any more hundreds that will fit in these groups. So now I'm going to move to the next place value, which is tens.
And I'm going to decompose those.
So let's regroup all of the hundreds into tens and put those into my 27 groups.
Okay.
I'm left with 8 tens and 1 1.
Okay.
Again, I can't put any more tens in, so I'm going to regroup those the 8 tens for ones. I have 81 ones, which I will then place into those groups to get my final quotient of 263.
Yeah.
Another model that you might see is the partial quotients using an open area model. You want to make the connections back to multiplication when you're finished with this.
I see the multiplication there because I'm thinking about it's an open area model.
Yes.
It's got length and width. The that 263 is, if I think of that as the length, that's the quotient, and my divisor is the width. So the area is the actual dividend.
Correct.
I see it. I see the connection between multiplication and
if we
division.
want to make the connection back to multiplication, my factors would be 27 and 263.
Exactly.
And here would be my product.
Yes.
Which are the pieces that I removed from the total of 7,101.
Which is partial
division.
quotients, yeah. Mm-hmm.
Looking at another partial quotients model, I might first have my students create a little help box and do some skip counting by the divisor. You see on the far right the skip counting from 1 group to 9 groups of 27, and all of the partial products or the products of those factors on the right hand side. I can use that then
to have, like I'm seeing here, the expectation is at this point that a 5th grader would understand patterns.
Correct.
And multiplication. Mm-hmm. But if I know that 27 times 2 is 54, then I know that 27 times 200, which I see in that traditional algorithm, is 5,400 or 5,400. I see that there.
Correct. In this partial quotients model, you can see that we've taken 200 groups of 27, 60 groups of 27,
I'm sorry, partial
3 groups
quotients
of 27.
Yeah.
You're okay. On this slide and the next, we're going to look at the traditional algorithm that you and I grew up with. We've still got the same partial quotients.
Yes.
We just recorded a little bit differently in the traditional algorithm.
Much more abstract, but the misconception is that students think they're taking away 54. Well, that's where the place value language has to come into play. It's really still 5,400 or 5,400s. The same with that. I'm not taking away 162. It's 1,620. So that those zeros hold place value.
Correct. So I'm thinking in this one, I'm thinking how many groups of 27 will fit in 71 hundreds.
Yes.
And 54 of those groups, or
Yes.
I'm sorry, 200 of those will fit into 7,101.
Yes.
Going back to the base 10 model, we want to make connections between that base 10 model and the traditional algorithm. So I can see that I have 200 in each one of my groups, which is where the 2 in the quotient at the top comes from. But those hundreds, if I count them all up, all of the hundreds that are in those 27 groups, I have 54 of them.
So if you literally just count 100, 200, 300, you're going to have 54 of those flats.
Yes.
Or 5400s. I see that. Yep.
So my 200 groups of 27 gives me my 5,400 or 54 hundreds in that model.
Yes.
Same thing with the 162. That isn't 162. That's 162 groups of 10. And if I were to count up all of the 10 rods that I see in my base 10 model, there are 162 of them in that model.
And 162 times 10 is 1,620.
Yes. And then we see our 81 ones. There are 3 in each one of my 27 groups.
Yes. As with any benchmark, we can always think about the CRA process as an instructional practice. Concrete, we're taking out those base 10 blocks and building those area models. We connect that then to open arrays that you see there on top, moving into that partial quotient strategy also with an open array and seeing the connection to multiplication. And then abstract, you see some different algorithms there that students can use if they have deep conceptual understanding.
Students should have had the bulk of the concrete in 4th grade, but we want to make connections between the concrete, representational, and abstract thinking.
That's the key.
So getting those blocks back out to help make those connections will be very beneficial in your classroom. Thank you for joining us for this edition of Math Dive in 5. We'll see you again next time.